this if it, there we go. Okay. So we're going to finish up doing some chapter 7 problems unless you guys have stuff that you want to specifically ask. Let's stick to chapter 7 for right now. So at the end of Wednesday, we went ahead and did delta H problems like doing Hess's law, delta H of formation. So now I kind of want to hit a few other of the points from that same chapter so that we can kind of wrap up that review, and then we'll go back to 12. Okay, so does anybody have any, and I can give you a minute to check, but do you have any chapter 7 problems that you've come across as you're hopefully starting to study and do the practice exams? Okay, so at the end of class, we were doing this reaction with delta H of formation. So I just copied down the reaction itself and the delta H that we determined. That's supposed to be a negative. It's not very obvious. Maybe I need to just draw that in a little more. Okay, so I want you to answer these first 2 questions, and then we'll talk through them, and then we can go on to the next one. Okay, so it's referencing this particular reaction that we did before. Feel free to flip back to your notes if you're like, I don't remember this stuff. So I'll give you maybe, shouldn't be too long, 3 or 4 minutes to do this. Okay. You guys ready to go through it or a little longer? No responses.
Are we just doing D and E?
Yep. Good? Okay, I'm just going to go through it unless someone objects. All right, so the first thing to remember, and this is more of a concept thing, and maybe we can talk about a couple of the other concepts as part of this, but since this is a negative delta H, we know that we're going from a high potential energy to a lower potential energy, and this amount is what's being given off, okay? So you'll see these energy diagrams with the little activation energy hump. You'll see that sometimes. You might also see them just like reactants and products. Okay, so if the products are lower in potential energy, then that means that that energy was given off somewhere, and that's when you see that negative delta H. That's the heat that's being given off. So as part of this, probably a good point to talk about the signs of heat and work, because I don't think I have a specific question that covers that. So Q and W, if you remember, are kind of the two big concepts that we talked about at the beginning of how energy is transferred during a chemical reaction, or really during any process. Okay, so the heat, we're going to do one of these problems in a second, can be calculated with, if it's a really simple process, can be calculated with mass times specific heat capacity times the change in temperature. And for a lot of instances, we will actually use the enthalpy, particularly when we're talking about a chemical reaction, in order to describe the heat change in energy. Work is negative P change in volume, so negative pressure. So just adding that negative sign on, not negative pressure, but negative times the pressure times the change in volume, where volume is V final minus V initial. Same thing for delta T, T final minus T initial. Okay, so those are two different types of calculations you might see. You could see one of these where it's adding together those two quantities. And then we could have some conceptual questions that stem from that. Okay, so there's a slide in the notes that talks about this very detailed, but overall, you want to know that a negative Q and a negative work both mean that energy is leaving the system. So this could be a gas, it could be a piece of metal, it could be a chemical reaction. Those things could all be part of this, not part of the system. Those things could be the system in different problems. Okay, so realize it kind of spans the gamut as far as really simple systems to lots more complicated systems when we're talking about a chemical reaction. Okay, so both of those, when it's a negative, it means energy is leaving the system. Another way to think about that is that the reactants are at a higher potential energy than are the products. If it's going down in potential energy, that energy must be leaving the system. If it's going up in potential energy, that must mean that energy has to go in. Okay, and that's going to be represented with positives on both of these. So positive Q or positive work would be energy into the system. Now, you could have instances where like you had a negative Q and a positive W. So that just depends on kind of their relative scale, right? Are they the same amounts? Is one bigger than the other? That would be a situation where you'd have to actually have real numbers. The other way we phrase this with work is when we say it's leaving the system, that is work is done by the system. So the system is the thing pushing on something, doing work, and the positive W would be work done on the system. So the surroundings is pushing in on the system, putting energy into it. Trying to think if there's other kind of little details associated with this. When you have something that has a negative Q, a negative heat, and relate this to exothermic reactions as well, it's going to feel hot because you are feeling the surroundings. You are the surroundings. So if there's heat coming off of a reaction, you're going to feel that in your hands if you're holding whatever, the container or the heat pack or whatever it is. With a positive delta H or a positive Q, it's going to feel cold. This one always confuses people because they're like, well, if it's absorbing heat, why doesn't it feel hot? Well, because you're not touching the chemical reaction, you're touching the surroundings. So it's taking heat away from you in order for that increase in potential energy. And in reality, it's not the chemical reaction absorbing heat and leaving it as heat, it's absorbing heat and turning into potential energy. Okay, so there's lots of good, more detailed stuff in the notes about this if you want to go back and review it. But this is just a good point to, like, you know, during review days, it's like reminding you of the stuff that we kind of talked about in class so you don't forget topics. Okay, so second one, it says, what's the enthalpy change if 1.6 moles of hydrogen peroxide is reacted with excess N2H4. So this particular value is for this reaction. So it's for 1 mole of N2H4 with 7 moles of H2O2 and so forth. Okay, so what you need to do is do a stoichiometry problem. But now, instead of converting from moles of the H2O2 to moles of something else, like in, you know, chapter 4, we would have been looking at how many moles of water can I produce, or how many moles of nitric acid can I produce. Here we're asking how much heat can I produce. So we just use the coefficient from the balanced equation with the heat value, the enthalpy value, and that's how we get the enthalpy for that amount. Because we know for 7 moles of H2O2, it's going to be this negative 1371, but we don't have 7 moles, we have 1.6 moles. So this is going to be an enthalpy of negative 313. And with 2 sig figs, I would probably write that as negative 310 on the exam. Okay, let's go ahead and do this next one. This is heat capacity. And we're going to do both A and B here. And I'll just let you read through it, take a shot at it. Good mix of calculation and concept together. Yes. Well, I am recording it. Okay. There you go. Yeah, definitely. Yeah, so I always hesitate to record every single class, but I have been for the last, literally this entire unit, I think. So if you guys if you want to go back and look at either the practice problems or stuff from previous classes, it's all on YouTube. Yeah.
So it's asking for the specific heat of the metal, but we're only given the final and the initial of the water and the initial of the metal. So how would we get the final of the metal?
So you're given the final of the two together because you're putting them together and then they sit there, so they end up at the same final temperature.
Okay.
So, yeah, so that 26.29 is the final for both the water, for both the water and the metal. Did that answer your question? I think that was, okay. There's actually two ways you could solve this. I'm intending you to do it the easy way. If you wanted to look up the heat capacity of water and do it that way, in theory, you could. No, that would be like totally a waste of time. So, never mind. So I'll just start putting up the work. If you want to finish doing it on your own, that's just fine. And I'm going to subscript all of these with an M for metal, just because the next question asks about water specifically. Okay, so I actually could have given you this problem. I wouldn't do this on the test, but I could have given you this problem and not given you this amount of energy, because you know, or at least I would have told you, that the specific heat capacity of water is 4.184, and you have the temperatures of the water. So if you were to, oh, but you don't have the mass. I lied. Okay, never mind. I'm not gonna tell you, oh, and then I could give you the mass, and then we could do this. Like, that's too much. That would basically be a totally different question. Okay, so you take the heat. Now, if you forgot to put the negative, all that would have happened is your answer would have had a negative value, and specific heats aren't negative. So you can just ignore that. So a specific heat should always be positive. If you get a negative value, you probably just messed something up with either the change in temperature or you forgot to change the sign of the Q. How did I know that it was negative? Because it says it emits that amount of heat. And this is really the key for finding the answer to question B, because if one thing is emitting heat, the other thing has to be absorbing it. There's always an exchange of energy. It doesn't just go away. So if the metal gives it off, the water takes it, and that's why it's positive. This kind of relates back to the concept of you can do this for energy. In this instance, you can do it for heat because we're assuming that no work happens. But the energy of the system is always going to be opposite the energy of the surroundings, because it's an exchange. You're not getting rid of any energy. You're just giving it to somebody else. The other way that you know that the Q is positive for the water, or for that matter, that the Q is negative for the metal, is because the temperature is dropping for the metal. So that's another indicator that it's losing heat, and the water is increasing in temperature. And so that's another good indicator that it's absorbing heat. Okay, so really it's a matter of making sure you know that absorbing heat is going to be positive and emitting it is going to be negative. So I'll give you a minute to just jot down any additional stuff that you need to from this. And then I think what I'll do is I'm going to open up the notes for chapter 7 and just make sure that I'm just going to kind of scroll through them quickly and make sure there's not any other topics that kind of didn't jog in my memory as I was picking out these problems. So after teaching this stuff for 20 years, I was a TA 20 years ago. So after teaching this stuff for 20 years, I have lots of random practice problems, and none of them they're not all perfect as far as like doing it the way that we did it or the depth. So I just randomly go pick problems from old files. This was an old exam. Okay, am I good to switch this? Anybody still copying anything down? Okay. All right, so pulling back to the notes, just gonna look through these. Talked about Q and W. We talked about exchanging energy. We didn't really look at these, but I think it is something, just to be aware of, like gauging the exchange between things. I don't really use this a whole lot. I tend to use energy diagrams more. But this is a good one for understanding the relationship between system and surroundings. So like maybe the way I would word this more in a question is, if your system has an energy loss of negative 20 joules, what's the change in energy of the surroundings? It's positive 20. Okay, there's always got to be the exact same value, but an opposite sign. And that's what these are trying to represent as well. We didn't do a ton of these. Oh, I don't remember who that was, but somebody was so mad because one of the questions on there was a conversion between calories and joules, and a calorie is different than a calorie. So the big C calorie is what we're talking about with food calories, and that's actually a kilocalorie. So the reason we do that is because if we didn't, then an apple, instead of being 100 calories, would be 100,000 calories. And that's just not something that, the everyday person is going to be like, oh yes, I have a, diet that is, what would that be? 2 million calories or something. Anyway, so just be aware of that. We didn't do a ton of these conversions, but you should be able to, do a simple conversion. The only one that we did that really is important is liter atmospheres, because that's how work is typically given. So let me just show you a quick example of that. Just did one of those. Okay. So when you do work questions, you end up using atmospheres for the pressure and almost certainly liters for the volume. So that means that the unit that you get for work is liter atmospheres. And that's not what we use for heat, and that's really not what we use for any other energy unit. So you're almost certainly going to need to multiply that by 101.3 joules per 1 liter atmosphere. That's in your exam equation sheet. If it isn't, I'm sure it's in the question. But just be aware of that, because you can't add Q and W unless they're the same unit. So they need to both be in joules. I think I did just about everything else. Okay, so let's go ahead. We skipped this in case you're looking through your notes and wondering. So let's go ahead and switch over to chapter 12, unless anyone has any additional questions they want to ask about 7. Okay, last call for chapter 7. And then chapter 12 ones that have come up as you've been studying or reviewing at all. All right, we'll just do these practice problems that I have then. Okay, so if needed, go ahead and draw Lewis structures for each of these. In fact, it might be a good practice. I don't know. Do you really need that? Whatever. Do it if you feel like you need it. And then you are going to identify the strongest attractive force, meaning intermolecular force, in each of those substances. So, once you get those intermolecular forces, why don't you like rank them? So let's say 1 is the weakest and 3 is the strongest. So ranking them from like increasing strength. Yeah.
Is there a reason that there's not a hydrogen? Oh, you just drew resonance structures. Never mind.
No, not resonance structures. So these two, is that what you're wondering about?
Yeah, why there's
Yeah.
no hydrogen?
So when it writes the structure with the oxygen and hydrogen next to each other, like in the second one, the C2, this one, it is telling you that the hydrogen is bonded to the oxygen. When it separates them and puts like all the hydrogens together, it's telling you that the oxygen is not bonded
Oh,
to.
we were drawing. I didn't.
Yeah, yep. So these are isomers. So same number of oxygen, carbon, hydrogen, same formula, but just the structure themselves are different. And we may have done these ones actually, these two specific examples. So I would writing them like that, you should know that the oxygen's not bonded to the hydrogen there. Or I would give you the structure itself and say like, I don't know which one has the highest boiling point or something. I'm going to change those questions a little bit. Okay, so this is, I would say, a review type question. It's pretty straightforward. Anybody remember why do they talk about similar molar masses? What does that have to do with it? So, yeah, go ahead.
Isn't it like the higher your mass is, the higher the boiling point?
So it's specifically for one of the types of intermolecular forces. So the higher masses will have higher London forces, induced dipole forces. So if you had compounds that were all induced dipole forces, which this one is, so this is, we'll say London because it's easier to write. So this is just London forces. If you had something that was just London forces and you're comparing 2 or 3 different molecules, then you need to look at the molar masses. But in this instance, that isn't really relevant because this one is dipole-dipole and this one is hydrogen bonding. And so we know pretty much off the bat that this is going to be our weakest one, and then this, and then that. Yeah.
I don't think I quite get why the ether doesn't have hydrogen bond.
This one here. Yep. So, because you have to have the nitrogen, oxygen, or fluorine bonded to the hydrogen. So they can't just be in the same molecule. They have to actually have a bond. The reason is because the hydrogen bonding comes about because there's a big difference in electronegativity. So oxygen and carbon only differ by like 1 unit, whereas oxygen and hydrogen differ by like, I think 1.5 or 2 units, it might even be 2. So that bigger difference in electronegativity is what's responsible for the increased intermolecular force strength. And that's why it's so important to draw the structure, because if you just see, oh, there's hydrogen and oxygen in there, then immediately you're like, oh, it's hydrogen bonding. Yep. Okay, so I'm gonna veer off. Now, I'll just tell you, like, you should know that this one should have the highest boiling point of the 3. And number 1 should be the lowest. What about if I asked about the delta H of vaporization? Okay, so this is the energy required to go from a liquid to a gas. So these are like actual values, joules of that energy transition. That is also going to increase with increasing force. So once you can order them by their intermolecular forces, so like let's just say C3H8 is less than or weaker than CH320, which is weaker than C2H5OH. Once you can order them in that, you can also say that this is in order, so this is increasing intermolecular force strength. You can also say that this is increasing the energy required for vaporization to occur. You can say that this is increasing in boiling points and melting points. And even a step further, this is increasing in surface tension and viscosity. Thinking if there's any other liquid properties we talked about. The only thing that we did not call it vapor pressure. What did we call it in here? Evaporation, just like a rate of evaporation. The only thing that is reversed in that would be rate of evaporation. Just in case you read the term, or if we did talk about it, I feel like I didn't use that term, but vapor pressure. That's the only one that is opposite. So increasing would be the other direction. It would be inverse to the strength. Because if they're stronger, it means they stay together better. And evaporation or vapor pressure is where the molecules are actually separating from each other. So that's inverse of their strength. So the weaker they are, the more easily they're going to evaporate or turn into a gas. I think I have one other in here that I just need to tweak slightly, but I think it's a little bit more involved because these are all like the carbon-hydrogen compounds, which we do a lot because they're so common, but also because they're really good examples of it. Like I mentioned before, if you had just carbon-hydrogen compounds, you can, first of all, you know that if it's just carbon and hydrogen, that it's nonpolar and therefore London forces. But you can off the bat, no, that's not what I wanted to do. It's 4, 5, 6, yeah. Okay. You can off the bat know which has stronger London forces simply by its molar mass. So this guy's gonna have the strongest of London forces versus this one because it's larger, it has more electrons that are shifting around. And then if you remember when we talked about hydrogen bonding, we also talked about the fact that additional hydrogen bonding sites, so like when you have multiple OH groups on something, that's going to increase the strength as well. So like sugars, for example, typically have like 5 or 6 different, even just like simple sugars, like 5 or 6 different alcohol groups, OH groups on them. And that's one of the reasons why they are solids at room temperature versus like a typical alcohol that's a liquid at room temperature, because they have those additional hydrogen bonding sites. So within hydrogen bonding, you can rank them based on how many of those little OH or NH groups do they have. Within dipole-dipole, it's really based on which one is more polar, but those are kind of hard to figure out, so we don't talk about them a ton. And then within London forces is how massive they are. The bigger they are, the stronger those forces will be. Okay, last question. So number 6 here. So we did not talk about, these guys very much. So maybe I will put, thinking, those two are the solids. So we will just get rid of those. I want to add something in here though. Sorry, I'm thinking. All right, why don't we add in like, so ignore this thing about what's a liquid, what's a solid, etc. I just want you to predict which are more likely to be gases versus which are more likely to be solids. Okay, and I'm gonna add on, so we've got CO2, C3H8, CH3CHO. You're gonna wanna draw the structure for that. Thank you. And then let's say C18H38. Did I add in helium? Oh, I thought I said helium, and helium. Okay, so those 5 compounds, I want you to rank them, starting with the ones that are most likely to be gases, and put them in order up to the ones that are most likely to be solids. You can go, Riley. You don't need to stay. Of course. You too. Now on the exam, I feel like I would probably give you the structure for this one, but I just wanted to let you guys push yourself for a minute a little bit more. When we look at this structure, like initially it looks like the oxygen and hydrogen are bonded to each other. However, that carbon, the first one has its 3 hydrogens and then the bond to the carbon, and we know carbon's gonna form 4 bonds. So the only way that carbon will form 4 bonds with this structure is with a double bonded oxygen and the hydrogens over there. So I would probably give you the structure for that. Or in this particular example, it doesn't really matter because this guy is going to have the strongest forces because there's only one that isn't London. All 4 of the others are London forces or induced dipole. This one happens to be dipole-dipole, but it's the strongest whether you thought it was dipole-dipole or whether you thought it was hydrogen bonding. So this one is the most likely to be a solid. It's not going to be. just telling you. But like, we're assuming at room temperature. We could say at a given temperature. So I guess if you, lower the temperature enough, it will be the first one to solidify. And all of the others are London forces. So that means we need to look at their masses. Okay, how do I know? Because this is polar bonds, but they cancel, so that's nonpolar. This is just carbons and hydrogens. Same thing with that one. Helium is all by itself. It's what we call an atomic solid, if it's a solid, but atomic forces that are holding it together. They're just London forces though. So helium is the lightest one, so it is most likely to be a gas. Let's see, C3H8 is probably lighter than CO2, 12.01 times 3 plus those 8. Oh, those are really close to each other. Did we have another one that was using these two exact ones? This looks shockingly familiar. Okay, those two are basically the exact same. So C3H8 has a molar mass of 44. Carbon dioxide is right around 44 as well. So there's no differentiating between those two. And then it would be C18H38 because that's your largest one. So I can tell you this guy is a liquid at room temperature, and these ones are all gases. So just like intuitively, I know that, but you don't have to know that. You can look at those intermolecular forces to guess that. Okay, so the weaker the forces are, the more likely they are to be a gas because they will break apart easily. The stronger those forces are, the more likely it is to be a solid. Okay, and then the rest of the stuff in 12 is pretty much the phase changes, doing those calculations with heating curves and cooling curves, the phase diagrams, which we've done just earlier this week. So we probably don't need to do a whole lot of review on that, at least not in here. Okay, so both practice exams by Sunday night, obviously exam Monday morning. And yeah, I'll usually answer questions if you guys have them, especially if it's like on Saturday. I'm sure I can get it back to you. See ya.